Well, good afternoon again. We're going to talk about section 13.2 right now. You see, we have this concept. It's how you start Calc 1. It was called limits, and you learn to loathe them. Loathe is the right word until you really learn them. Think, okay, this isn't so bad. So here's what we're going to do. We're going to talk about limits and continuity of multivariable functions. We'll see how this works. What I really want to focus on for about the first 20 minutes is what it means. What are you doing when you're finding a limit? Because if you understand the concept, how we're going to do the rest of it makes a lot more sense. If you don't really get what we're doing, like why are we doing this, then they're not going to make sense at all. You're just going to have a set of rules that you're going to go through, probably never really get it, and then eventually make a whole lot of mistakes on it. Make sense? So I want to focus on what a limit means when we're talking about multivariable functions. Let's start with something that we know. Let's start with something about limits with functions in one variable. And what we mean, of course, when I talk about variables, I mean independent variables. So when we have a function of one independent variable, what we get is we get this curve on a plane. That's entirely what we have. One variable, two dimensions. Remember talking about that from a couple times ago or last time? One variable, two dimensions. So if this is my function, I say, well, how does a limit exist if we have a function in one independent variable? We go, well, it exists if this limit equals a number. Yay! And it doesn't exist if that equals like an asymptote and they're going opposite ways, or if we have different values. But more specifically, we say here's what has to happen, and this is the big part, okay, because this is going to change when we get to multivariable functions. Here's how we recognize that limits exist for functions in one variable. We go, well, you know what? You know it. How do we tell that limits exist for functions of one variable? What do we do? Evaluate. How do you evaluate them? What do you... If I say, does the limit exist here? Does it exist at the point P? Yes or no? Why? Why does it exist? Does it exist at the value P here?
No.
Okay. Why?
Because not both sides.
From both sides. So we have this idea with limits of a left side and a right side. You guys remember that? It's a long time ago, I know. And that's how we determine that limits actually exist. We say, okay, well, if this limit exists, what that implies, or how we got that, was that the limit, as we approached along the axis of the independent variable, from the left to a certain value, and from the right to a certain value, were the same. So we do this. Hey, let's come. Now here's the big thing. Here's the big thing. This is what matters. Where do we travel? What do we travel along when we're checking the limit of a function of one variable? What do we travel along? Well, okay, so we're moving this way, but we travel along the actual curve. We don't travel along the x-axis, because if in both these situations, let me make them a little bit more on top of each other, okay? So let's see. Here's the x-axis, here's A. There's two different functions here. There's top function, bottom function. Say, hey, what's the limit as we approach A? You don't go like this. You don't go, A, done, D for done, D for done. That's what you mean, D for done. We don't go this way. That's not what we do to check limits. What do we travel along when we are evaluating our limits? Think back to what a limit means. A limit means, what's the height of your function? What's the function value? As we're approaching that number on that axis, that's what it means. What it implies is that we're approaching that number on that axis from both the left and the right. And the height of our function has to be equal for that limit to exist. You guys understand that concept? I don't want to have to go back and reteach Calc 1, but I will. Pause right now, we'll watch the videos. Just all of us together. It'd be awesome. Look at to soothe my voice. It hurts, man. It's hard work. That's what it means. So, do we actually travel along the x-axis? No. No. We travel along the curve. That's what we travel along. So we go, okay, here's how we do it. From the left, what's the height of my finger as we get close to our vertical dotted line, which is at A? Okay, it's right here. What's the height of my finger as I get close to that vertical dotted line? It's at the same height. That's how we know where a limit exists. What's the height of my finger? It's over here. As I'm traveling along the curve, approaching this x value dotted line. It's right here. From the right-hand side, traveling along the curve, it's right here. Wait a minute. Those things are different. The height of my function, the height of the curve, is different as I'm approaching the same x value, x-axis, from left and right. Limit doesn't exist. Limit does exist. Show of hands if you're okay with that one. Okay. Now we extend the concept. Okay. Let's consider something else now. This happens if this happens. The limit exists if from the left and from the right we approach the same value on our function. Now, what about this? What has to happen for a limit to exist if we have more than one independent variable? Well, there's an issue, right? The issue is a very huge ambiguity right now. Are we traveling along one axis of one independent variable? The answer is no. What we need to happen is that order. Do you remember doing this from last section? If you know, you got to go back and kind of remember this. But what we're doing here is we're plugging in an ordered pair. That ordered pair is along the xy plane. We're plugging in that pair. The ordered pair is giving us a height above the point on the xy plane. Does that make sense? So we have to traverse this plane. We have to traverse the plane now and see what's the height doing as we're traversing this plane. Well, that means instead of approaching one number on one axis, we're approaching one point, but we're doing it from what? From what? From what direction? How are we doing this? What is the curve in this case? And this is the whole situation. How do we know this limit exists? Well, if it equals L. Done. Yay. That tells you nothing. It tells you nothing. Here's the issue. And we just covered part of it. What's that give you? What's a function in one variable? What's it give you? Come on. Gives you a curve, what you said, on a plane. This is just a curve on a plane. That's all it is. What does, and this is the whole reason why I had the last section, so you get really good at this, okay? What does a function in two independent variables give you?
It's a curve.
It's not a curve. That's the whole point. If it was a curve, it'd be easy. We'd have Calc 1 again. Done. One variable, you need how many dimensions to graph it?
It's 2.
Don't make me drop this one dimension, okay? I'll do it. Drop it like it's hot. Two variables. How many dimensions do you need to graph a function with two independent variables? That means it's a surface. You remember just talking about this? You go to a point, you get a height. My voice is getting squeaky. Come on, don't do that to me. You go to a point on the plane, you get a height. A lot of different heights creates a surface for you. What we're talking about on this situation is what's the height of the function doing as I'm allowing my point to get close to here. But there's a big problem, and here's the problem. Surface. Point. Other point. How you feel all the time in this class. Just kidding. Let's say that this is my point. All right, this is my point right here. This is the point AB, or well, the height above the point. So you got to imagine that this is the height. The whole idea here, the point, is that this point is on a surface. Here's my question. if the limit here says, and this is the whole reason why we did it, you have to travel not along the axis, but along the curve. What's the height of the curve doing from both directions? What's the height of the curve doing from both directions? Well, that gives you one path. You see, on a curve, there's a certain path. There's only two ways you can get to this value, from the left and from the right. That's two ways. If they equal from the left and from the right, we say that's it. That's only two ways you can get there. There's no magic third way coming from imaginary land, all right? This isn't Harry Potter with a math wand. Done. That's not what we're talking about. There's literally only two ways. So when we're doing this, we say, okay, for one variable, it's kind of comfortable. I think I'm going to have a balloon all the time just because I rest my arm right there. Perfect. For one variable, this is a curve. It's a curve. It's a certain path. There's only one path. And what that means, the whole important thing about this, the reason why we were able to find limits so easily in Calc 1, is there are only two directions you can take to get to this value. You can go from the left and you can go from the right. There's only two directions you can take to this value, from the left and from the right. So that limits us to two directions. I'm going to say point, what I mean is the value. I'm going to say point just so it makes a little more sense for this. But here's the whole idea. With one variable, you have one path. You have a certain path. There's only two ways you can approach that value, that point. From the left, from the right. Show of hands, you understand the concept. Here's the idea now. You've got a surface. I say, tell you what, I want you, this is the function, all right? This is what this means. You already told me that two independent variables creates a surface. Let's pretend this is it. And I want to let my points, my things that are creating this height, get to that value. How many ways can I approach that? This is the surface, right? Yeah. Which means that my function is traveling along this. How many paths can I take to get here? Imagine this is a mountaintop, and here's a little cabin. That's a horrible cabin. And you say, hey, I want to get to my cabin. And there's no roads. Pick any road you want. How many roads can you take to your cabin? I could do this, right? I could take that road. Or I could take this road. Or I could go this way. Or I could start over here and go, I like Smiley. I'm going to show Smiley. I'm not drunk. And I go what? Back over here. Here's my question. How many paths along your surface, how many paths along your surface could possibly get you to that point? How many? Infinite. That blows this thing out of the water. There aren't just two paths anymore. Curves, you guys get the idea that curves are two paths. Left, right, done. On surfaces, how many paths? Wow, I completely kind of functioned that thing up, didn't I? Really effed it up. So how many paths can you take to get to a point? An infinite many. You could go left, doesn't make sense. Right doesn't be up, down. You could go infinitely many paths to get to this point on a surface. Do you guys understand the idea? Let's write out a couple of those ideas, and then I'll show you what we can do and what we can't do. So for two variables, it's no longer a curve. This function is a surface. And the problem is there's an infinite number of paths along that surface that could intersect that point, that could get to that value on the function. I know I've talked it for a while. I said I was going to talk about it for about 10 minutes just so you understand the idea. It's going to take another 10 minutes before we get to well, maybe not 10 to do our first example and why we're doing that. But do you understand the major problem between one variable and two or more variables? Instead of one where you have only two directions, now we have an infinite number of paths that's getting us to our point. Infinite number. Here's the problem. If you wanted to prove that the limit exists on this surface at that value, you have to prove that along all of those paths, they get to that point. Is that easy to do? Do you want to write out all of the paths? You literally can't, because there's infinite many of them. There's infinite many vector functions, curves, that are on the surface that go here. Infinite many. Right? So how do we do it? Well, it's really hard to do. You should read that. Impossible in most cases to do that. We can do it with something called the squeeze theorem. Calc 1 concept, we're going to use it again. All right, we'll do it later. It's hard. It's not that easy to do. I'll show you how you can prove that limits exist with the squeeze theorem. Do we generally do that? Not really. Here's why. It's a lot easier to do two things. One, it's a lot easier to prove limits don't exist. It's really easy. Left side doesn't meet right side. Or one path doesn't meet the other path. It only takes one example, and you can prove a limit doesn't exist. You guys understand the idea? To prove something is true, you got to prove it for all the cases. To prove something's not true, you just got to unprove it for one case. Done. So a couple things about this, and we're gonna get through it here in a second. So to prove that this exists, you have to prove that along all the paths, we approach the same height as we approach that point. All paths, all infinity of them. We get to prove that along all paths, we approach the same point. Really hard. Squeeze theorem would do it. We can use squeeze theorem. I'm going to come back, I'm going to prove that, but that's going to be the end. But it's not easy in general. Sometimes it's impossible. We just can't do it. So, how do we prove these things exist? One of them is squeeze theorem. The other way is that we use a lot of the principles about functions that we know. For instance, we're going to talk about continuity. If you remember from Calc 1, if you have a function that's continuous, the limit has to exist at every single point. Do you remember talking about that? Say, hey, it's continuous here. Continuous, no jumps, no gaps, no holes, no whatevers, nothing that makes it undefined. The limit's going to exist at every single one of those points, and it will equal the function value at those points. We can use stuff like that. So we're going to use continuity to help us out with some of these limits, to let us evaluate them really quickly. That's pretty nice. So we can do that. So squeeze theorem is one way. Using some of the properties of limits from Calc 1 is another way. Other than that, we can easily, relatively easy, prove when a limit doesn't exist. It's really akin to what we're doing here. From one direction and from another direction along the curve, we're equaling a different value. That's the idea. On a surface, it's from one path and another path, we'd equal a different value. I can't show you with this because this is and we're going to show this a little bit later. This will be continuous at any path. because it's defined everywhere. There's no holes. There's no asymptotes in 3D. Those look weird. But there's nothing like that. Asymptotic planes. There's nothing like that. So this will be continuous everywhere, which means that all the paths lead to this at one point, at that point. So that's okay. But in general, it says this. It says just find me two paths that when we approach my point, xy, it gives me a different height. I'm going to say that one more time so it sinks in because some of you guys are zoning out already. All right? I'm going to say this. Find me two paths that when I get to my xy, when I get to this, it gives me out two different heights. That is what this situation would be in 3D. You go, hey, along one path, I'm up here. Along another path, same surface, I'm down here. Okay, that right there tells you you're not continuous at that point, and therefore the limit does not exist at that point. That's what we're doing. And it only takes two paths. Because if we can show two paths don't equal the same height, that right there is enough to say the limit doesn't exist. Why? Because for the limit to exist, we have to show that every single path goes to the same value. If we prove that two don't, we've proven that wrong. That's the point. So we can easily prove a limit does not exist by showing that along two paths, we get a different value as we approach the same point. Did I spell approach wrong like 14 different times? I did. Sorry. I don't even know which one it is anymore. You ever do that? Like you know it's one way, but then you write it two different ways and you can't tell anymore. I'm pretty sure these two are wrong down there. Don't ignore those. Just white them out on the whatever. Draw it in there. Typical math teacher, right? Typical. They shouldn't even let me write words. I don't even know where I'm at anymore. What was that? Approach. Thanks. That's really helpful for us. We get okay. We get a different value. The different value is the height of your function. It's on the surface. F of xy as we approach the same point. Xy. That's a horrible xy. I really don't feel like explaining this anymore. Have explained it well enough if you guys understand the main concepts. One variable, easy, don't exist. Done. One variable, easy, exist. For two variables, not easy. You have to prove every path goes the same, has the same value. Not easy to do. To prove it doesn't exist, it is easy. Just prove at least two. At least two paths have different heights when we are getting to the same x value. So here, xy. What's going on? From one way we're up here, from another way we're down here. Those are different heights. Limit does not exist because we failed that. Show of hands feel okay with that one. Let's do a quick example. Some of these are very easy to do. I'm going to show you exactly how you go about telling what you should do and when you should do it. Just to kind of recap a couple things, ladies and gentlemen, how many independent variables do you see right now? Very good. Everybody, come on. How many independent variables? 2. What would this graph look like? 2D, 3D, 4D? 3D. This is a surface in 3D. What I'm asking you is, does the limit exist on this function? So, is the height of this function, so the surface, continuous at that point? Do we have continuity? Do we have the limit existing from every path? Can we go to the same place? I don't know. What I'm saying is, at this particular point, as x and y, the point approaches 0, 0. From what direction? It's on a plane, ladies and gentlemen. There are no directions. Any direction you could get to 0, 0 on the plane. You can think about it that way, too. Here's a plane. Here's 0, 0, the origin. On the plane, how could you get there? infinite number of ways. There's not just one axis, there's not just one direction. Make sense? Also, I don't like that band, One Direction. But anyway, it's the wrong direction. So, can we prove it exists? Listen, I'm going to cheat. I'm going to tell you some backwards things that we're going to get later, but you use them now. So I'm going to teach circularly. I don't even care anymore. I'm going to kind of use something that I'm going to prove later, and then I'm going to use that thing to prove it later. So it's going to be a little circular. Here's the deal, because I just want you to be able to do it pretty easily, and we're going to use continuity to do it. The first thing you should do every single time when you get a limit from back from Calc 1 is what?
Plug it in.
Just plug it in. Just see if it actually works. And we're going to use that later. So try to plug it in. Now what do you get? 0 over 0. L'Hopital's! Oh crap. Can we do L'Hopital's? Do you know how to take derivatives with two independent variables?
Yes.
You do? How? Oh crap, you have physics, don't you? You suckers. Not yet. Next section, yeah, changed a little bit. It's weird. But no, because what would you do with your partials, right? Partial derivatives, what are you going to do with that as far as your limit's concerned? All that would do, because all you know right now from your physics class is that there are these things called partial derivatives. Some of you do not even know what they mean yet. You just know that you have to do them, and this is how you do them. What they will do for you is they will give you a path that is over a certain axis. That's all they do. They limit your travel along a surface over a certain axis. I will explain that next section. So, will they help us? They could, but not generally. No. What we do is, first you try to plug in, you get 0 over 0. You go, okay, well that's a problem. If it worked out to a number that's defined, done. You're done. I'll show you why later. We'll talk about continuity later. But you'd be done. Here's what we're going to try to do now. What I'm going to ask you specifically for is show that this limit does not exist. Not try to prove that it does exist, because it's not going to, but show that it doesn't exist. How? How many paths do we need to prove a limit exists? Infinite. How many paths do we need to prove a limit doesn't exist?
2.
So let's pick 2 paths. I'll tell you something right now. Always pick x or y equals 0 as one of them. That's the easiest path. Now I'll show you that. So we're going to put along. Along x equals 0. Oh man, I need another balloon. Along x equals 0. Here's what this does. Can you imagine this? So along x equals 0, imagine this at the origin with that point is right above the z, okay? So this is the axis. Here's what's happening. If I let you do x equals 0, x equals 0 goes way back here. Then what's the only variable that we have left? Because I asked you. Oh, that was funny. Come on. Yeah, it's y. I know. If I let x equals 0, then I say let's force that to be 0. We would be traveling along the y-axis. Please notice something right now. I'll explain it a little bit later as well. I'll reiterate it. But notice something. 0, 0 is along the y-axis. Do you see that? We have to. Whatever we restrict, it's got to be a solution. Have that point as a point on that line. We have to do that. We can't go, I'm going to go over here. We got to travel over whatever we're restricting this to. So if I say, let's let x equal 0, then what this implies is that I'm going to be approaching that point. Point down here, here's the function value, but only along the y direction. So this would be the curve that's doing this. Say, I'm going to take the path where x is 0. That's right along, I'm going to try to do it this way so you see it. Right along just the y direction. Just right over or under the y-axis. Do you guys get what I'm talking about? So if I let this go along x equals 0, what about the z? The z is the height. I don't have to worry about that. That's a dependent variable. I'm only worried independent. So if I let x equals 0, what I'm doing is I'm traveling over the surface right over the y-axis. Did you guys get that? So this right here is traveling along the surface directly over the y-axis. Not the x. X equals 0 is not over the x-axis. X equals 0 is over the y-axis. Now let's see what it does mathematically. If I force x to be 0, look, stop writing, just look for a second, okay? If I force x to be 0, what happens to my x's? They are 0. The only variable that now changes is the y variable. That changes our limit completely. If I go along x equals 0, all my x's are 0. This limit now becomes a limit of, what's on the numerator? If x is 0, well, you know what, we'll do it. How much is x?
0.
But wait for it. As what approaches what? Is x approaching anything anymore? No, we don't even need it because x is fixed. So what that allows us to do is basically take a 3D limit and change it into a 2D limit. Or take two independent variables and make it, let's see, which one? This one. Make it one independent variable. So instead of x, y approaching 0, 0, forget it, man. I'm already stuck here. I've already let x go to 0. I'm just along that path. Of course it's going to hit x equals 0 at some value, at some time, somewhere along my surface. But now I'm only letting the y change. Does that make sense to you? If I'm along the y, man, I hope it's sinking in. If I'm letting along x equals 0, that's literally solely above the y-axis. Do you guys get it? Which means that the only thing that can be changing is the y. I'm right over that. That's it. Let's make it easy. Negative y squared over y squared. I don't care how fast or slow you do your limits at this point. Once we change it here, you're done. If you want to match degrees, which is always a great idea, you can do it. If you want to do L'Hopital's 2 times, fine. Divide by a large power denominator, I don't care. What are you going to get out of this thing? Perfect. That was heaven saying, I love these answers. No, it's just Adam's phone. It's okay. Question. Did that prove the limit exists?
Yes.
Have we shown every possible path? We've shown one. The one that's right. Let's talk about every possible. I don't have infinite time to do that. We have one path right here. All we have to do is show one path so it doesn't exist, all right? That's literally the point. Show me one other path. Along, what do you think? Intuitively, what do you think? Let's try that. Why don't you set that up? As you're writing this, I'm going to say a little blurb. Along y equals 0 shuts down the y-axis. It forces you to only travel the surface right above your only other independent variable, which is x. So this would be traveling the surface right along the x-axis. That's it. It would give you this. So if this is the y, the x would be traveling this way, so traveling on the surface, but right above the x-axis. It'd be trying to give you this idea. Now, what I'm going to try to show you here is that these things don't match up. On this graph, or on this balloon, they would match up. This would not be good for us. I'll show you what to do in that situation in just a minute. Did you at least let your y value go to 0?
Yes.
If you do, then this is 0, this is 0. These are still x's, but since you let y equal 0, you're right above the x-axis. The x-axis is your only legitimate independent variable left. You're saying if I'm over the x-axis, the x-axis is the x variable is the only thing that can change. So I don't have this anymore. I just let x approach. Do you see why x would still be approaching 0 though? I still need to make it to that point. I've already taken y equals 0. So it's gonna, whatever path I do, is gonna make it through that y equals 0 value, but I also want x to go to 0, because I need to make it to 0, 0. Those two ideas have to be kind of cohesive. Does that make sense to you? I just did a whole lot of words, and so we're like, if you let y equal 0 already, and change this all so it's only x squared minus 0, okay, done. Over 2x squared plus 0, done. You're trying to get to that point, correct? You have to make it to that point. If y equals 0, I now need to say, okay, I know my y is 0 right over x. I need to let my x coordinate approach that 0 value so that I hit 0, 0. Make sense? We should do it one at a time. How much is that?
1/2.
You have just shown this situation on a surface. It's practically the same. It's just that from this way and from this way, you're getting two different heights. There's infinite paths, but I just need to show along the surface, along two curves, two paths, that I get different heights at one point, just above one point. And that's exactly what I've done. So by showing that along two paths, what paths? Right over the y-axis, right over the x-axis. Along those two paths, I have a different value for my surface, and that says the limit does not exist. Because along all paths, we have to come to the same value for our function, or same value for our surface. Show of hands feel okay with that one. So we'll wrap this up here. Say you showed in your test. You say, hey, -1 does not equal 1/2. Therefore, the limit does not exist. Please be very careful on your verbiage here. The limit doesn't exist at what point? 0, 0. At the input 0, 0. Other points? Sure, it's going to exist. Most other points. Can I give you a couple hints that's going to really help you out? Here's the quickest, easiest, simplest way to do limits, or to show that limits don't exist. But you've got to listen carefully because I'm not going to write a whole, I'll write a couple things out, but not a lot. Check it out. Ready? Ready? Cover up your y's, do the limit in your head, you get 1/2. You see it? Cover up your x's, do the limit in your head, you get -1. Did you catch that? If those numbers are different, go along x equals 0 and y equals 0, done. Because that's exactly what we did. We let the y equals 0, 1/2. We let the x equals 0, -1. Different values, different height, done. Just show your work. Go along x equals 0, y equals 0, and you're done. Does that make sense to you? That's the easiest way to go about it. The problem is, what happens when we go along x equals 0 and y equals 0 and we get the same value still? And that's the nature of the next couple questions that we have. So a few notes. And we continue. So number one, try x equals 0 and y equals 0 first. In your head, don't even write them out yet. Just in your head, just cover up the variables and see if you get different numbers. If you do, then only x equals 0, y equals 0. That's it. That's all you got to do. So try these paths first. The reason why is because you can do them in your head very, very fast. That's why. listen carefully. This is not going to work all the time. If it doesn't work, so that means you do x equals 0 and y equals 0 and you get the same value still, have you proved something exists? Have you proved something doesn't exist? No. That's the worst case scenario. Then you go, okay, well, what do I do now? Try another path, but always use one of these to do one path. Okay, so always use one of those. If these don't work, choose other paths. A few notes here. There's a couple that I want you to know that are really going to help you. Number one, whatever path you choose must contain that point. That has to be the case. Why would you go, okay, I want to check the limit at 0, 0, so let's go through 5, 2. Yeah. Does that make sense? No, you want to make sure that path actually contains that point. So number one thing, make sure the path you're choosing contains that point. Does x equals 0 at some point contain 0, 0? Yeah. When x is 0, and then when y becomes 0. That's why you got to go along y, okay? So make sure that happens for any substitution you make, any path you choose. Be certain your point is actually on your path. Second, when you're doing this, it often helps to substitute so that the degrees on your numerator and denominator become the same. And thirdly, for one of your paths, always choose one of these. Always choose one of those, because it's the easiest one we can do. So always pick one of those if you can. Almost 99% of the time you can. It generally does not matter which one you do. I would like to try just 3 examples. We'll talk about having more than 2 variables. We'll go to 3 variables. After that, we'll talk about continuity, and that wraps this section up. Sounds like only a little bit. It's going to take us a little while, because I want to fully explain this. Again, limits, as you know from Calc 1, right? Limits are one of the fallbacks for people. They go, I hate limits. Why? Because I don't understand them. I want to make sure you actually understand this. Do you understand so far what we've been doing for real? Don't just nod your head and go, yeah, I get it. Do you actually get the idea of what we're doing?
Yes.
The over the surface, along the surface over a particular path. You guys get that? Okay. So let's try this. Let's do the limit here. There. Everyone in class right now, how many independent variables do you have? Okay, so this is going to be a what type of? It's a surface, 3D surface. Great. What point are we approaching? What should you do every single time with the limit, no matter what? I don't care what class you're in. What do you do with the limit? Just try to plug it in. What are you going to get here?
0.
Okay, well, that kind of sucks. So we can't just plug in the value because we get 0 over 0. We don't really know how L'Hopital's rule works. If it does work, We don't even know. So goodness gracious, what are we going to do? Well, what I'm going to ask you here is not to prove that it does exist, prove it doesn't exist. That makes your lives easier because all you need is how many paths? 2 paths. You can't do one. It doesn't make sense. You got to show that we're getting different values, just like from left and right side, we're getting different values. So if we need 2 paths that go. Here's the cover-up method that I would encourage you to try first off. Okay, check it out. Cover up your x's. What's the limit there? Oh, silence. Oh dear. Okay, that's good.
Yeah.
You know what? We got to use one of those anyway. So let's try x equals 0. Let's see what happens. Can you at least left-siders, can you tell me what I should rewrite if I'm letting x go to 0? Tell me, please.
Anything you want. Just plug in 0 correct.
So just do it. Tell me what it is.
Limit y.
Oh, a limit. Oh, good. I still have those. Good. What variables do I have?
Y.
Where's it going?
0.
Can you verify something for me? That this point 0, 0 is somewhere along the y-axis, which is x equals 0. Can you verify that for me? It's somewhere along there. You have to have that happen. If it doesn't happen, you're wasting your time. What happens when I let x go to 0?
You get 0 squared.
Over?
Y squared. Y squared.
What is that?
0.
It's 0. 2 ways you can prove it. 1, oh wait. How many independent variables do you have now?
1.
Does L'Hopital's rule work?
Yeah.
Now it does. Easily. You have 0 over 2 if you want to do L'Hopital's rule twice. Fine. Or you just go, well, that's an actual 0. This is only approaching 0. So it's 0 divided by an actual number, not 0. Keep in mind what limits do. They say, I'm getting really close. So that's 0 for sure. Head nod if you're okay with that one. You can do that by just going, hey, let's cover this up. Can you still do L'Hopital's rule? Yeah. You get 1 over 2y, which is 0 over 2. It's 0. Now try this. What if I cover up the... should be on this side. What if I cover up the y's, let y equal 0? Do I still get 0?
Yes.
That's a problem. And I'll show you right now. If I go along y equals 0, then I'm fixing the y. I still need the x to go to 0. Notice 0, 0 is along that path. If I let y go to 0, then I still get 0, but I have 3x squared. Do you guys see where the 3x squared came from, where the 0 came from, yes or no? How much is that limit?
0.
Now, if you didn't get it the first time, let's get it this time. I got 0 along this path. I got 0 along this path. Does it prove the limit exists? How many paths can get to this point? Infinitely many. It's the origin on a plane. Infinitely many lines, paths, curves, whatever, get to that value. I've shown 2 that exist. Have I proven that the limit exists? Have I proven the limit doesn't exist? Which is my question anyway. I've done nothing. I've done nothing so far. Now, not nothing. One of these is good. Okay, this is at least one path. Now, both of them are, you don't need both, but choose one of these because it's really easy to find. So either one, I don't care. But it's not enough. Verify that this is not enough for me, please. Let's pick another path. Here's how to pick the other path. First, be certain the point you pick is actually on your path. We're going to do that. Substitute so that this is the big one, so that the degrees of the numerator and denominator are equal, and always use either, okay, we already got that one down. So here's the other path I would choose. I'm going to look over here, and I'm going to choose, you know what, I'll make a little side note. I'm going to choose so that this happens. I want to pick y equals a function of x, or x equals a function of y. I'm going to pick that. But I want to do it so that these conditions are met, so that I still have this as a solution. It's got to be there, and so that my degrees are are equal. There's multiple ways to do it sometimes, but here's the one I'm going to pick because I like setting y equal to x's. You guys get that? So check this out. Let's imagine something. Let's imagine if this y was actually an x. Could you multiply those?
Yeah.
What would you get?
X squared.
If this y was actually an x, could you add those? And you would get 4x squared. Do you see how I'd be matching up the degree of the numerator denominator? That's real nice. That's what I'm looking for. Also, just so it sinks in, so you get it. I probably don't have to explain it anymore, but just so it sinks in. Notice something. If you were to graph y equals x, look, if you were to graph y equals x, is that a curve? Yeah, well, okay, we call lines curves. Is that a curve?
Yeah.
Does it go through that point?
Yeah.
Ha! Can you make a substitution? If you did, you go, okay, well, what's the only variable remaining now? If I let y equal x, I have a limit. I have 3x times, what am I letting y equal? Notice how you could do it the other way around. You could let x equals y. It doesn't matter. But just change it so you only have one variable. Why? Well, because we know how to deal with limits with one variable. Does that make sense? So, oops. Let y equal x. Let y equal x. Seriously though, are you guys okay with that one? Now, if we're only in terms of one variable, I really don't need to let y approach anything. I let y equal x. That's fixing the y. That's fixing it to the x value. It's making it now depend on the x, which means the only thing I let float around is my x. And it still has to go to 0. It's still got to approach that same value. For real, yes, no? Are you picking up what I'm trying to lay?
Yes.
Now let's do this. So here, if I change this, make it a little bit nicer, I got a limit 3x squared. We're not going to waste time doing limits real slow. What's that limit? By a variety of techniques. Now here's the question. Does that prove that the limit of this function at that point does not exist? Does that prove it?
Yeah.
Along one path we got to 0. Along another path we got to, well, that didn't prove anything. Along a different path we got to 3/4. Since 0, choose either one, I don't care. Since 0 does not equal 3/4, that proves that the limit does not exist at x equals, or as the function approaches 0, 0 on the xy plane. Tell you what, I'd like to do 2 more since we're right on this. They're going to go a little bit quicker. Since we're right in the middle of this concept, and when we come back from our break, I'll talk about how to deal with 3 variables. It can be a little bit easier because you don't have real nasty substitutions and you'll have this idea down. Are you guys ready for this? So let's try one more to get. You know what? Tell you what, I want you to try this one on your own. At least the first couple steps of it. Let's see. So as I'm erasing, here's what I would like for you to do. I'd like for you to go along the 2 paths that we pretty much always start with. Okay, well, actually, I want you to plug in the number. What are you going to get? 0 over 0.
Yeah.
So that means, okay, I want you to prove that this doesn't exist. right now, how I want you to start these, I want you to either in your head or write out these paths. If you can do it in your head, do it in your head. But you got to write at least one of them. You always have one of those paths. So I'd write this one out, and I'd go with x equals 0 and see what happens. Then in your head, or write the y equals 0, 1. If you got different numbers, you're done. If you don't, then you got to pick a different path. That's the hard part here. So I want you to try the x equals 0, y equals 0 thing, see what you get, and then work on finding a different path. Let's just stop for a second. I know you're still working. I know you're probably thinking about that path right now. At least I hope you've made it that far, so far. Let's think about this. If I let x equals 0, I'm traveling along the y-axis. 0, 0 is on the y-axis. That's great. I also know that 0, if x is 0, that's 0, the whole thing's 0. Gone. If that's 0, I get y to the 6th, and this is settled. If I let y equals 0, the only independent variable left is x. It still has to approach 0. I know that y equals 0 still contains that point. I know that y equals 0, that's 0. That's 0. We get 2x squared, and that's 0. That does nothing for you. That gives you about 1 point out of 10 on a test. Because what have you done? Literally nothing. You haven't done anything. You haven't proved it exists. You haven't proved it doesn't exist. You've done nothing. So let's pick another point. Let's do this. Let's try to pick a substitution that not only contains this point, but makes the degrees the same if we can. That's what I want to do. So let's see how to do that. If we're going to try to make the degrees the same, here's a little hint I'm going to write down. Maybe you should write it down. Take the variable with the smaller degree and try to make it into the variable with the larger degree. Otherwise, it's kind of hard. Because if I want to change, well, what's got the larger degrees here, x's or y's? Y's do. If I try to change y's into x's, I'm going to have to cut powers. Does that make sense? It's hard. It's easier to grow powers. So if I say I want x to equal something in y such that the variables have the same degree, can you see the substitution right now? What is it?
X y to the third.
Good. So I'm going to take the smaller degree variable and try to change it into having that power. So if I say I want x to be equal to, did you guys get the concept that I'm going to have to eliminate a variable, right? Because I can't do this stuff in two variables very easily. So I'm going to have to eliminate one. So I'm going to change x's into y's or y's into x's. I also want to do it so that my degrees become the same. Because the limits are way easier that way. The limits, you just basically cover them up. So I'm going to say, hey, let's go along the path x equals y to the third. Do you see why we might want to do that? If I let x, if this is a y to the third, that's y to the sixth. If that's a y to the third, that's y to the sixth, and I can add them. And then it's very nice, very easy. Should fans feel okay with that one? Also, one more thing, you gotta double check this. Is 0, 0 on that curve? Notice it is actually a curve right now. It's not a line, it's a curve through space. Is it on that curve?
Yes.
0 equals 0, done. So that says that if we let all x's change to y's, y to the thirds, then this is y to the third times y to the third times cosine y to the third. X was y to the third now. X is y to the third now. If x is y to the third, I get y to the third squared plus y to the sixth. Oops. What's the only independent variable left? So let's let that y go to where it's supposed to go to. For real, show of hands if you're okay with that one. It's kind of a weird one. Are you guys back there okay with it? You sure? Right side? I don't want to lose you. Okay, we spent too much time doing this for me to just lose you now. This would be the kind of funner stuff, interestinger stuff. It's a word. Can you simplify it? Let's try it. How much? This is 2y to the 6 plus 1y to the 6. We get 3y to the 6. With me? Yeah, no. Can you simplify that? Ladies and gentlemen, this is why we try to make the degrees the same. Because if we can do some basic math operations. Gone. Get them gone. That's great. Oh my gosh, sorry. Why do you people let me do that? Goodness gracious. I just like 3s today. I don't know. Wrote so many of them, that's why. So we're left with cosine y to the third over 3. What do you do every time in Calc 1 when you do anything with a limit? What do you try over and over and over again? What should you try now? Plug it in. Hey, what's y to the third if y is 0?
0.
What's cosine of 0? Does that prove anything?
Yes.
Okay, everyone, what's it prove?
Limit does not
Why?
exist, is that
Why? Because along those two paths, this one a curve along the xy plane, which we're floating on. This is weird, right? This is like S curve. So we're floating on the surface above that S curve, and we're getting to this value, that point. We're getting to that value, and then we're right above either one of these axes, and we're getting to a different value. So the height of the surface is a different value as I'm approaching along the surface over those two curves. So since 0 does not equal 1/3. Limit does not exist at that point. Yeah, yes, no. Okay, tell you what, one more. I'm basically just gonna do this one for you. I'm gonna talk through it just to show you some weird things that can happen, because this doesn't tell the whole story. We're not always going to 0, 0. Your substitution is not always going to be x equals y or y equals x. It's not how it is all the time. So I want to do one more at least to give you that. There we go. What's the first thing you do with limits, like all the time? If we plug that in for x equals 1 and y equals 0, do you see, maybe you can think about it for a second, that we're going to get 0 over 0? X is 1, so that's, well, in the numerator you get 0, 0. But down here we got 0. We got 1 minus 2 plus 1. That's 0 over 0. If it wasn't, you'd be done. Just plug it in, you'd be done. We'll talk about y later, but you'd be done. Just plug it in. So since we get 0 over 0, we go, well, let's show this limit doesn't exist, or let's try. Everyone in class right now, what path do you use at least? What path do you use? You use at least one of these all the time. What is it? Well, either one. Either x is 0 or y is 0. So pick one. In this case, I think I did y equals 0. So if y equals 0, we got limit. Oh, wait a second. If we're going along y equals 0, this is 0 and that's 0, that's true. This is 0, I get x squared plus, nope. I get that. Can you tell me where the x should be approaching? Is it true that along x equals 0, I'm going to hit x equals 1? I'm going to hit this point 1, 0. Notice that y equals 0 is the x-axis. Do you guys get that? So that point is on the x-axis, 1, 0, it's on there. So I'm going to be going through that point. But you do got to make sure you go to the right value. So x still has to approach 1. Since I'm fixing y equals 0, x still has to approach 1. Should finish feel okay with that one? Okay, so what's it give you? It gives you 0, not 0 over 0, it gives you 0. Because if you do L'Hopital's or whatever you have, you actually do get the 0 out of that. Now, if I go along, let's just see if you're paying attention. Should I do it? Should I? Why? Can't hear you guys. That point's not even on that curve. Does that right there go through that point?
Nope.
Then don't do it. That's silly. You're wasting your time. You're wasting your time. What about this? Would that be something I could do?
Yes.
Yeah, that goes through that point. That's fine. Now let's just try it in our heads, okay? You don't have to write it out, but try it in your heads. If you did, if x equaled, you know what? Fine, write it out. I don't care. Y would have to go to 0 if x is 1. We get that. Because we have 1 minus 2 plus 1, you get that. The only independent variable left is y. Y has to approach 0. I got 1 here, so we get, what's that limit? Come on. Does it do anything? So we need another path. Now, sometimes to get your path, because right now it's not obvious. You go, man, I have no idea what path I should take. Because if I go try to match up variables, I start having 1s here. That doesn't really help me. If I let x equals y, that doesn't really help me. I get some squares. Do you guys see the problem that I'm talking about? Are you sure? So here we go. Y equals 0, done. No problem. X approaches 1, got to go to the point. X equals 1, got to go through the point. Y's got to approach 0. Either way, we get 0, 0. It's not telling us anything. Sometimes some tricks like this help. Not tricks, but some simple math. Try factoring. See if you can factor this stuff. Sometimes that gives you a path to go along. For instance, if I factor, and if I factor this, pull the y squared, but notice how x squared minus 2x plus 1, it's still here. That's a perfect square trinomial. In fact, it's x minus 1 squared. Oh, shoot. Hope you saw the little change there. You guys okay with that one? It should be a plus. It should be a plus because you have y squared plus this. This is that piece. You should have a plus 9 times. Does that make sense to you? I know it's just algebra, but just algebra is what messes you up, so be careful with that. Should finish okay with that one for real. Okay, now, if you have that, you go, well, how about this? Is there a path that I can go along that's going to make my degrees the same? Notice I have power 2. I've got a power 2. I've got a power 1. I want a power 2. And these are the same. How along that path? Let's change a whole piece of it. Let's change that ugly piece. If we change that ugly piece, we go, hey, let's just change x minus 1 into a y. And now if you're okay with that one. Now stop right now. Stop. Let's see. Is this point actually on that path? Plug in the 1 for the x, plug in the 0 for the y. Does it equal? X. 1 minus 1, 0 equals 0. You know that point's on that path. Does that make sense? It's going to work. So let's see. We'd have limit. Let's talk about an independent variable in a second. Am I still going to have a 2y? I don't want to replace the y's, okay? I want to replace this. Am I still going to have a 2y? Am I still going to have an x minus 1? What am I going to have?
Y.
This is a y squared plus, if this is a y, that's also y squared. What's the only independent variable I have left? Come on, folks, quickly. And what's it going to? 0, because x, we fixed x along this path. So we said along the surface, over this path, and now we're letting y go to 0. The x is done. X is tied up in the y's. We don't have to worry about it. It's just this independent variable that's moving now. We get 1. Big fat 1. Question, did it prove anything?
Yes.
Come on, put it together. Why? What did it prove? Does not exist. Why?
Because 0 does not equal 0.
What's it mean? Why is it not?
0 does not equal.
I know that 0 doesn't equal 1 and 1 doesn't equal 0. You're saying the same thing.
Because at that point they'll have different heights.
Yeah. Because what?
At that point they'll have different heights.
Different heights. That's all I'm doing. Along these two paths, different heights. That's it. Limit doesn't exist. So 0 does not equal 1 because these are the heights of the function along those two paths, along the surface over those two paths. So along the surface over those two paths, the function has different heights. Therefore, the limit does not exist. At that certain value. Do you feel like you fully understand this concept up to this point?
Yes.
Because limits can be tricky. But I've given you some good techniques here. We've shown how to show limits don't exist. When we come back, I'll do 3 variables. We'll talk about how to do that with 3 variables. We'll talk about continuity very quickly. And then I'll do the squeeze theorem and show you some pretty pictures. All right, so how do we do this when you have more than 2 independent variables? We made the transition from 1 to 2. 1 is easy, calc 1. 2, I showed you how to prove limits don't exist with 2. Now we'll talk about what happens when you have functions with 3, count them, 3 independent variables. What type of a surface is that? 4 dimensions. Now that's weird because the paths now are in 3 dimensions. Does that make sense? So we're traveling along. Here we were. Oh, sorry, I rushed it all. In one independent variable, you were along a curve. Basically, you only had 1 dimension of travel, left, right. That's it. With 2 independent variables, you had 2 dimensions of travel. We were on a plane, and then surface said you're restricted to these 2-dimensional curves that we're traveling above. With 3 independent variables are curves. They're still curves, but they're space curves. They're now in 3D. Well, what's nice, it's actually nice, it's not hard. What's nice, don't overthink this. We're not traveling along surfaces. We're still traveling along curves over these 40 surfaces. But for 3 variables, the paths are now parametric because that's how we defined curves in 3D. They're now parametric. Does that make sense to you? And that's what we're going to be traveling over paths in 3D that are parametric curves. Quickly, everyone, what variable do we use for parametric curves?
T.
So your whole goal in life right now is to replace x, y, and z with t. That's literally all we're going to be doing for one of these things. That's it. We're going to be traveling along those paths. Now, this is nice. Some people don't talk about this. Talk about this. Always choose an axis as one of your paths. Always choose an axis as one of your paths because it's really easy to do that. So I want to show you how to choose an axis, then we'll talk about how parametrics play a part in this because otherwise it looks really confusing. So let's start this. So the first thing I want you to do is go along an axis. What axis do you want to go along? X. Love it. Let's go along X. I want to explain what's going on. We are in 4D. The curve, the surface. Sorry, not the curve. The surface is in 4D, but we are traveling along that surface over paths in 3D. Just like in 3D, we were traveling over paths in 2D. Do you guys get it? So we're going to be traveling along this weird 4D surface over a 3-dimensional curve. That's what we're trying to describe right now. One 3-dimensional curve is simply the x-axis. That is a curve in 3D, isn't it? It's a boring one. But how do we describe it? Well, if we're talking about x's, y's, and z's, how do we get the x-axis? What's the y value for anything along the x-axis? What is it?
0.
And what's the z value for anything along the x-axis?
0.
So it's really easy. Just set y and z both equal to 0. That's probably the easiest thing we've done all day. Just set both x and y equal to 0, and you will be along the x-axis. Head nod that you understand that. So what we're looking at right now is what's the value of the function, the 4D surface, as it's traveling over the x-axis. A 3D curve through space. That's what we're doing. So if we do that, the limit is, hey, if we let y equals 0 and z equals 0, we have 0. Oh, so that's 0, 0, 0, 0, 0 over what? And what's our only independent variable left, ladies and gentlemen? And what's it got to approach? How much is this limit?
0.
Perfect. That's why we always choose an axis first. If we can. That's why we choose an axis first. Because it's really, really easy. You just set y and z equal to 0, or x and z, any two of them, and you're traveling along an axis. Should fans feel okay with that one? You can choose z-axis here because z is now an independent variable, unlike before. Okay, it's independent, so we can do that. You guys understand the concept of doing this? Weird concept of we're now on a 4D surface, and the path that we're over is a 3D path. So, what's the other one? Well, the other one, we're going to have to go along a curve that's parametric. The biggest piece of advice I can tell you is set all of your variables equal to a function of t, because that's a parameter, such that your degrees match up, just like we've practiced. So we're going to go along a curve, call it C. Go along a curve where, well, let's look at it. I'm going to replace x's, y's, and z's with t's. What's going to let the powers match up? Well, what I'm looking at is, this is x squared, y squared, and z squared. If x, y, and z all become the same variable, will I be able to combine that stuff? Let's just let x and y and z all equal t. X equals t, y equals t, z equals t. What is it? What is x equals t, y equals t, and z equals t? What is that curve? It's a line through space. That's all it is. Do you see the parametric line? That's what we're traveling over now. So in 4D, we're going to be traveling along the surface over that 3-dimensional line. That's it. That's why we use parametrics, because to travel 3 space, we need parametrics. Should fans feel okay with that one? Now let's make the substitution. If x and y and z are all t, then our limit becomes, well, let's see now. tt, t squared, t squared, t squared. Super fun. Hey, what now? Now this is an interesting question. What is now our independent variable, since we basically just parameterized this function? T. What's t approaching? 0. Not 0, 0, 0. Because if we watch carefully, if we let t approach 0, x and y and z also approach 0. So letting t approach 0 lets the point approach 0, 0, 0. Does that make sense? So just got to watch that sort of stuff. So t is approaching 0. So that's the limit as t approaches 0 of t squared, let's see, 3t squared over 3t squared. How much does that equal? Come on.
1.
Does that prove something for us? Huh?
Should that be 3t squared over 3t squared?
Oh. Yeah. One. It wouldn't have been one before. Sorry. What does it prove for us?
That it
That it doesn't. Why?
Does not exist
It's
at
different heights.
Because as I'm traveling along the 4D surface over that path, the x-axis, and over that path, which is a line through space, the value of the function is different. That's what we're proving here. Does it make sense to you? So, since 0 does not equal 1, the limit does not exist at 0, 0, 0. Please wrap this up, at least for my class. I want a statement, at least something that you actually understand the concept. Do not just say, doesn't exist. Doesn't exist ever? Come on. We just proved that because of these two paths, the limit doesn't exist as we approach that point. That's the idea. Listen, I'm not going to make it through the whole thing here. I just want to give you the blurb about how you start it. Don't worry, we started last time. What would you do first? If I wanted to prove this doesn't exist, what would you do first? Go along what? An axis. So you'd do maybe the x-axis, you'd get y equals 0 and z equals 0. You get 0 over x squared, you'd still get 0. Do you guys see what I'm talking about? What I want to focus more, so one of them along x-axis, and we would get the limit as x approaches 0 of 0 over x squared, and that's 0. That's still 0. That's an easy one. That's nice. You pretty much always do that. What I want to focus on is the parametric curve that I want to create. This is a little harder because you don't just do x, y, and z all equal the same parameter t. What I want you to think about, maybe I'm going to give you about 30 seconds to just think. Just think about it. How can I make these powers all the same? How can I make those powers the same? If I can, how could I do it? So think about it. What's the variable with the largest power right now?
Z.
Try this. Try calling the variable the largest power t. Let it equal t. Then try to make the other ones match up. So for instance, if z equals t, I would get t to the fourth. Does that make sense? I also want this to be t to the fourth. What would y have to equal in order to get t to the fourth? I also want this to be, bless you, t to the fourth. What would x have to be to get t to the fourth? That would do it. That would do it. If we do that, the limit changes to t equals 0 for sure. And we got t squared times, notice that, here's x is t squared, z is t, so t squared plus 2 times, oh, hey, t squared squared, because that's y squared. Then we have t squared squared, t squared squared, and t to the fourth. I guess I am doing the whole thing. I always do that. I should never say stuff like this. Can you double check my work? I did a lot of it in my head.
That's right.
Triple check?
That's right.
They're the same person.
That's right.
Doesn't count when you do it twice. Did you get the same thing?
Yeah.
Does it prove anything?
Yes.
0? 3/4. Not the same. Limit doesn't exist. Done. Show of hands feel okay with this one. Now we practice. Now we practice evaluating limits. I need you to know that evaluating limits is exactly the same here as it is for Calc 1, and I'm going to cheat. I told you I'm going to use some circular reasoning. What I'm going to do is show you how to evaluate based on the fact that we have continuity. Then I'm going to talk about continuity and use that to kind of fill in the fact that we're able to do this, okay? So here's the how. I'll talk about the why in just in a little while. So the how. Whenever we're evaluating limits, I don't care what class you're in up through calculus. The first thing I want you to do is plug the numbers in. Just plug them in. If you don't get 0 over 0 or a 0 on a denominator, you're done. Plug them in. And we're using the fact that if you plug in a value and you get a number, a limit, then that function exists at that point. And in a neighborhood around it, you can find continuity. And in a neighborhood around it, that means all the paths lead to that same value. That's what we're using here. We'll talk about if we have a domain that's defined, we're continuous on that domain. We'll talk about that in a minute, but that's basically what we're using. We're saying if this function exists, if it's defined at that point, you're going to be continuous at that point, which means that the limit has to exist, because if we're defined, the limit exists. If we're defined and continuous, the limit has to exist. Therefore, plug in a number, the limit has to equal the value of the function. We're kind of cheating here. The idea from Calc 1 would be if the point exists and the limit exists, and the limit equals the point, you have continuity. If you have this, the limit exists, the point exists, and the point's in that little spot, that creates continuity. So if we have continuity, i.e. it's defined, if it's defined, we have continuity. If we have that, then we can go backwards and say, if we have continuity, then the limit exists. And that's what I meant about we're going backwards here. So let's try it. Can you plug in your x and your y value? What is your x value? What's your y value? Have you already plugged this in?
Yes.
How much do you get? 3? Okay, 3. Y, well, 1, -2, okay, perfect. 1, -2, plug in, you get 3. Simplify, you get 3. You guys okay with that one? All right. Boy's a weird one. We also learned this from Calc 1. Right-sided and left-sided are super fine as long as you have continuous functions. So honestly, plug the numbers in and see if they work. So just plug in 0 and 0. Let's see if we can do that. Can you plug in 0 and 0? What do you get? Come here, folks. Just this part, just that. What do you get here? So something close to 0 from the right, positive. Something close to 0 from the right, also positive. You're going to get something close to 0 from the right, 0. So you're going to get 0, really close to 0, but positive. Reason why it has to be right-sided because you have it under a square root. You can't get that from the other side. Okay, so you can't have negatives. That's the only reason why it's there. So this is e to the 0 over -1. How much do we get for that? That's it. That's it. That's evaluated limits. Head nod if you're okay with that one. We can make them nastier, but the idea is the same. So let's try, I'm going to give you one that's kind of nasty, and then I'll give you another one I want you to think about. So give it a try. Here's x, y, z. I want the limit of the following function as we approach the point 0, 3, 1. And the function is oh, don't worry. Worry. Yeah, that's what I'm talking about. Woo! What's the first thing you do with any limit, like ever? Can you just do that? Just plug it in. Just plug it in and see what happens. Hopefully I wrote it down right. I'm sorry. after you do that one, I want you thinking about the next example, please. What's the x value?
Sure.
Y value? Z value?
1.
Instead of trying to do all of this math in your head, probably not a good idea, at least write out some pieces of it. All right, so for here, I'm writing out e to the sine of, I do know that's 0, so I'm going to put the 0. E to the sine of 0 plus ln, that's got to be there, cosine, that's got to be there, pi, that's got to be there. But I would do things like this. 3 minus 1 is 2. So this is times 2, or you can put 2 pi. Does that make sense to you? I do just little stuff, not a whole bunch. It's crazy too hard to do that. How much is sine of 0?
0.
How much is cosine of 2 pi?
1.
How much is that?
1.
Plus?
0.
Equals? Limits 1. Okay, yes, no. Easy, medium, hard. Plugging stuff in pretty easy as long as you know to do that. Now, did you think about that one as we were doing the problem? Did you think about that one? What's the first thing you always do with limits? Plug it in. What does it give you?
0.
Crap. Every other time we tried to prove this doesn't exist. Now we're going to try to prove it does exist. There's a few ways that we can go about thinking about this. One of them is a squeeze theorem, which we're not going to do right now. We'll do it a little bit later. One of them is squeeze theorem. Another one is, well, you can do some algebraic manipulation, or you can do a really cool trick sometimes that helps a lot. If it's not working for you, and you're like, dang, I don't even know, but you see a lot of x squared plus y squareds floating around. You see a lot of that. You see what I'm talking about? Number one thing, goodness, don't make me drink at night. Please don't start canceling this stuff out. I like crossing stuff out. I cross it out. Please don't do that. I swear, please. I'm baking. Please don't do that. Okay. Also, I don't want you to start factoring. You can't factor this. It's impossible. You can factor that, but it's not going to help you. You get your x plus y times this quadratic that's not factorable. So you go, what am I supposed to do with that? That's not going to help. What I do see is that, goodness, I know that this is true. As long as they let, right? This and that also be true. Sometimes we can trick our problem into thinking that it's polar. Make it polar. If you get 0 over 0 and you see a lot of x squared plus y squared, 0 over 0, and you go, well, let's try to make this thing happen. If we do, we can let this go to r, well, x would be r cosine theta. So r cubed cosine cubed theta plus r cubed sine cubed theta. Head nod if you're okay with that one, for real. Yes, no, yeah? Do you see where this came from? If x is r cosine theta, then x cubed is r cosine theta cubed, r cubed cosine theta cubed. Same thing for the y. What's the denominator? What's it going to be? My next question, this is a really kind of interesting question. What's my independent variable? What's it going? What's x and y relate to up here? Say what?
Theta.
X and y are only tied. Well, they're tied to theta, but they're also tied to r. Well, let's see what happens. If x and y go to 0, 0, what's x squared plus y squared going to? Then r would also go to 0, but look, it can't be negative, all right? This is going to give us something that's positive, so plus, right-hand side. So if we're going to use that, then our r is the thing that's going to 0, but it's right-sided. Now, can you see something nice to do? Come on, quickly. See something nice to do. What are you going to do? Not yet. What are you going to do?
Simplify.
You're going to simplify. How? It's the F word. Come on. What are you going to do? So if we factor, and we simplify, let's think about it. I don't even care what this is. Tell me why I don't even care about that. What that is. What's the R doing?
0.
What's 0 times pretty much anything? And even if it's 0, I don't really care. So 0 times anything is how much? 0. Does that prove the limit exists? Yes. Yes, it does. We plugged in the number. We actually got a number out. That proves the limit exists. Head now if you're okay with that one. Question.
Why does the R have to go or 0 from the right again? I missed that.
Well, a couple reasons. When we're, man, you could go absolute value. You could go absolute value, but you're never going to get a negative out of that. The absolute value R, if you took the square root of both sides, you get the absolute value of that R. We just go 0 plus to not have to do with the negative, honestly. So that's why. Not a very big thing. Just make sure you go to 0. Can you do it for the next one? Can you see the substitution for the next problem? Because right now, if you plug this in, do you know what you get if you plug that in? Plug in 0, 0. What do you get? Come on, folks. How much is this?
0.
Times how much is this? This is 0. ln of 0 is negative infinity. ln, as you approach 0, negative. It's doing this. That's what's happening. ln of 0, negative infinity. This is an indeterminate form. If only. Indeterminate form. That's what that is. Well, if we start doing stuff like, all right, let's let x squared plus y squared equal r squared, then we can change our limit to r ln r squared. Quick head nod if you're okay with the substitution. Please don't let your r squareds change to r's magically. Don't do that. X squared plus y squared is r squared. Are you following the math on this? Do you see why our r is going to go to 0? Now, that doesn't help you with the indeterminate form, but if you ever did limits of indeterminate forms from section 6.7 from Calculus 2, then you know that at this point, if you have 0 times some type of infinity, and you create this complex fraction, you change the 0 into a different, you change it into a different thing, you change it into infinity. Now you have infinity. Notice this. What's 1 over 0? Oh, it's infinity. What do you do anytime you see infinity over infinity? Come on, hope you know this. Say what? L'Hopital's. So here, even if you move this down, L'Hopital's, how are you going to do it? Because you got two variables, two independent variables. How are you going to do that? But if we change it to one independent variable and we manipulate it, now you got L'Hopital's. I'm not going to finish it. I want you to finish it. Try L'Hopital's here. So kind of a cool idea. I hope you like this idea. I liked it the first time I saw it. I thought it was pretty neat. You go, what am I supposed to do with this? I don't know. Give up? No. Let's try to change it to polar. Let's make x squared plus y squared equal r squared. We got some substitution for x and y. Same thing here. As soon as we do that, even if we have indeterminate forms, you know what to do with one variable. You can start creating from 0 times infinity, infinity over, change it, make it a fraction, over infinity, and then L'Hopital's. Head nod if you're okay with that one for real. Comments, questions, anything? I can't help you if you don't ask, yeah.
So, like that.
Okay. Anybody else? Yeah.
How do you get 1 over r squared?
You force this thing down to a denominator. You force it. So you go, well, where do I want that? I want to create this.
So we're forcing it to get the indeterminate form, so you can do with something.
It's already an indeterminate form. What you're forcing it to be is a form that allows L'Hopital's. So you go, how do I move this to a denominator? Well, you could do r to the negative 2. That forces it, right? Yeah? You guys know about negative exponents? Okay. Well, what is r to the negative 2? Well, it's actually a complex fraction. Now you got it. Now it's infinity over infinity. You can't do anything with this. Please, I'm begging you. Don't go 0 times infinity. 0. Sometimes. That's D for done right there, though. D for done. Okay. Sometimes not. You gotta work with it. So you create this and you go, hey, let's make it 0 times infinity? No. Let's make it infinity over 1 times 0. That's infinity. Infinity over infinity, and then L'Hopital's. Okay, we gotta get on with this stuff. We're gonna talk about continuity right now. Listen, here's the rundown on continuity. A function is continuous on a region if at each point in the region we can find this little neighborhood around it where we don't have any gaps, jumps, or boundaries. So basically we say, if we have this point on the interior of a region, you don't have to draw this, I'm just going to explain it real quick. If we have a point on the interior of a region, you can always draw a little neighborhood delta. A little, that just means little neighborhood, okay? Just a little circle around it. And even if you get really super teeny close, you could still draw a little teeny circle around that. Does that make sense to you? You can define some points around it, which means that at that point that we can draw this neighborhood around, we can get to that point no matter what path. That means that we're continuous on that surface over that region. On boundary points, so if you're actually on there, you go, well, this looks pretty good, but these points out here don't look so hot. In that case, we say, you know what? We're going to restrict our paths. Just restrict our paths to all paths that come from the inside the neighborhood, like this. We say paths outside, don't worry about those paths outside. So boundary points are okay as long as we restrict our paths. All this basically says, I know I'm going speeding through it because it matters. It does matter. But it's easier than some of these definitions make it. Here's what this says. If you have a region, you have a function that's defined over this region, it's going to be continuous at any point in that region. Why? Because you draw a little circle around it that's continuous within that circle. That's why. On the boundary, you're still fine, because you can find some paths from inside the region that get there. In other words, all of this stuff says the following. A function is continuous at any point inside of its domain. That's all it says. Here's a domain. Here's a point. Continuous. Draw a little neighborhood around there. All the paths go to that point. No problem. Well, to get to that point by any path, it's gonna be there. There's no jumps. There's no gaps. There's no asymptotes. There's nothing wrong in that if we're completely define that domain. Same thing on the boundary. There's no jumps or gaps within this part of it. We can find continuity there. All it says is that a function is continuous at any point inside the domain. That's what I want you to write down right now. So as far as continuity goes, a function is continuous at any point inside the region for which it's defined. Domain. Well, how do we define the regions? Well, how do we do that? On what regions are functions defined? We already did that. It's called the domain. Find the domain. You find out where the function is continuous. Do you remember that back from Calc 1 when you're like, wait a minute, finding continuity issues? Remember the holes and asymptotes from Calc 1? You watch them on the videos, you probably saw that. But where we found discontinuities were exactly where we found domain issues. They were basically one and the same until we start restricting our domain. If we don't restrict the domain and continuity give you the same region. And that's what I'm saying here. I'm saying that a function is continuous at any point on the region for which it's defined. The region for which a function is defined to be the domain. This is its domain. And that's kind of beautiful. Because we get a lot of the continuity properties we had before, they still work. All we have to look for are the same exact things we looked for before. Holes, these weird things that would be like denominators equal to 0, negatives inside square roots. So just look for the same problems we looked for domain. Does that make sense to y'all? Okay, there's a couple things I want you to write down here. A couple things that we get to use. The first one, polynomials are continuous everywhere. Rational functions are continuous everywhere the denominator is not 0, and continuity holds for compositions of continuous functions. So just put continuity holds for compositions. So those are the three things that I want you to put. Polynomials, continuous everywhere. Rational functions are continuous everywhere where the denominator is not 0. Polynomials continuous everywhere. Rational functions continuous everywhere the denominator is not 0. And 3, continuity holds for compositions of continuous functions. This last statement is why I can't do the squeeze theorem until, like right now. We're going to do some continuity and then we'll talk about squeeze theorem. Because this continuity holds for compositions of continuous functions, I need that to prove it. So we're gonna do that in a little bit. Right now, I'd like to do one example, just one. Okay, by one I mean two. 2 examples about continuity. Then we'll take a break. We'll come back and maybe do one more. We'll do that squeeze theorem thing. I'll talk about compositions and that'll be it. Pretty close. I do want some more energy out of you guys, though. You're making me feel like I'm punishing you. Oh, crap. You do feel like I'm punishing you. Question: Where would domain issues, and so likewise, where would continuity issues exist on this problem? If anywhere, where would they be? Good. Polynomial, continuous everywhere. Perfect. Polynomial, continuous everywhere. Rational function, continuous everywhere unless the denominator can equal 0. Now here's my question: Can the denominator equal 0?
Not without imaginary numbers.
Do we have imaginary numbers? Thank goodness, no. So we don't even have those. So, are there any continuity issues? So this would be continuous on, let's put it this way, on all points. Continuous on all ordered pairs, x, y. Question?
F of x, y.
Oh, yeah, I'm sorry. Thanks for that. Head enough, you're okay with that one. How about this? What if What if I just do one thing? Is that still continuous? So notice the change, please. Is that still continuous on all ordered pairs?
No.
What's the one point that I couldn't have? 0, 0. So this would be continuous, and here's how you'd write that. Write continuous on any ordered pair such that that ordered pair does not equal the point 0, 0. That's how we'd show the continuity. Say, hey, anything works. Only one that doesn't work is when the denominator is 0. That's a polynomial. Can just everywhere, no problem. If it's 0, who cares? But this one can't equal 0. That only exists at one spot. That only exists when x, y equals the exact point 0, 0. That's my only discontinuity. Should fans feel okay with that one? Okay, here's the second example. Let me take a break. Please notice the compositions. Please notice that they're really not an issue as far as creating for you more discontinuities. All they do is they might have some within. So let's take a look at it. What do we know about this thing right now? Firstly, is e to the x continuous everywhere? E to the x is a function. That's continuous everywhere, for sure. Is x over y continuous everywhere? What's the problem here? What couldn't we have? Well, come on, quickly. What couldn't? So we can't let y equal 0. So y cannot equal 0. Tell me right side something else quickly. What else do you know about this thing? Could it be 0?
Yes.
So that's it. That's literally it. The only things we have here are x got to be greater than or equal to 0. Y cannot be 0. So we have any ordered pair such that x must be positive and y cannot equal 0. Since domain gives you the region where your function is defined, and since the region where your function is defined is what's giving you continuity, basically finding your domain is practically the same as finding your continuity in almost every single case. And that's what we deal with. We'll do maybe one more when we come back from a break, but I think we need a break here real quick. Show if hands feel okay with what we're doing so far. Okay. So a few examples. We're talking about continuity. What we're finding out is that finding continuity and finding the domain most of the time are pretty much one and the same. Huh, almost rhymes. I like that. So you're just looking for the problem issues. That's all we're doing. Now, that holds true for functions in 3 independent variables. So let's take out this domain. Here's the problem. Here, check out the continuity. Here's the issue. Just like a domain of 2 variables is on a plane, 2D, domain of 1 variable is on a line, 1D, domain of 3 independent variables is 3D, which means continuity is also a 3D issue. So let's take a look at this. Do we have any domain issues on the numerator? Yes or no? Denominator? Yes or no? What do you know about denominators? Everybody, come on, quickly. So I know that that's true. That's it. That's the only continuity issue we have, so write it down. We want all sets of ordered triples such that x squared plus y squared plus z squared cannot equal 4 if you add 4 to both sides. Head nod if you're okay with that one. Now, think about what this means. Think about what this means. Can you tell me what shape, I'm going to ask you what shape this isn't. What shape is x squared plus y squared plus z squared equals 4? What shape is that? It's a what? What type of ellipsoid? Since all of our numbers are exactly the same.
Or a sphere.
It's a sphere. Here's what this says. It says any point in all of 3 space will work. We have no discontinuities there except for this bubble of that sphere. All it says is that the points you can't plug in, all those points are on that sphere. Does that make sense to you? It's all of the 3D space. The discontinuity exists on that sphere. The points that create discontinuities are on that sphere. That's why we can't let it equal a radius of 2. So if fans feel okay with that one. That's it. That's all we're doing. It's just regular continuity. Now, what I do want to tell you, the statement 3 down here from a little while ago, continuity still holds for compositions, and parametrics are all compositions. So when we're going to try to figure out some continuity that has compositions in it, just remember one thing. You can't ever make domain or continuity issues better. You can only make them worse. That's encouraging, right? You can't fix a continuity issue, ever. Here's how to do some parametrics, some compositions, whatever you want to call them. Let's focus on finding h of xy such that this equals g of f of xy. In other words, what I want to do is, do you know how compositions work? No. This says take the f thing, put it in for the g thing. So take this entire thing and replace this variable and this with it. Do you actually want to do that? No, not really. All I'm worried about is what's the continuity going to be for this composed function that we're going to get. Here's how to do that. Firstly, find the continuity here, find the continuity here, and I'll show you how to work with it. What's the continuity?
All real numbers.
Great. Why? Well, I mean, I don't want to say all real numbers, all ordered pairs. That's a better way to say it because these are ordered pairs. So this is continuous on all ordered pairs. True or false? This is continuous on all t. Yes, no?
No.
Okay, what's it not continuous at?
Over 2 pi plus 0.
Say what?
Over 2 pi is less than 0 is
No, plug in anything you want. Can you do it? Can you plug in anything to cosine? Can you plug in anything to sine? Can you plug in anything to t? No issues. Oops. Continuous on all t. Here's what I want to tell you. If this, please watch carefully what we're going to do. You're not watching, you should be watching. Please watch carefully. We're going to be taking this function and plugging it into this function. Does that make sense? Everything would be ending with x's and y's. The t's would disappear. That's what this says. Replace t's with xy stuff. You get me? So lots of xy's. If this is continuous everywhere, and this is continuous everywhere, tell me where this is continuous.
Everywhere.
Everywhere. But we're going to be in terms of whatever that says. So h of xy, that's why it says xy, because you're going to be ending with xy's. This would be continuous also on all ordered pairs. Does that make sense to you, that track with you? Now let's try this one. It's a little bit more complicated. The first part's really easy. True or false, this is continuous on all xy. Yes, no?
Yes.
True or false, this is continuous on all t. Yes, no?
No, false.
Ooh. Continuous on t such that what?
Greater than 0. Or
Such that t is...
greater than 0.
Let's make it really simple. This says greater than or equal to 0. This just takes away the equal. So if fans feel okay with that one. Now, here's what's going on. When we find the continuity for h of xy such that this equals g of f of xy, what this says again, take your f function and plug it into your t function. Here's what that means. It means every place you have t, what are you going to have? You're not excited, you should be excited. Every place you got t, you're going to have what? No, you don't have xy. You're going to have an entire function. What entire function?
X minus 2.
This says for every variable in this function, you're going to plug in this entire freaking function. There and there. Does that make sense? In other words, you're going to let t equal x minus 2y plus 3. Does that make sense to you? Now here's the magic part about that. What do you know about t? Read it. What do you know about t? It's got to be greater than 0. So that means that t must be greater than 0. Therefore, this thing must be greater than 0. If you can see that substitution, then you got it made. Can you see how to get from here to here? T's going to equal this, right? Because we're going to take that function, plug it in for t. If t has got to be greater than 0 by what we have, if t's got to be greater than 0, and t equals this thing, then this thing's got to be greater than equal to 0. Why are we doing that in terms of x, y? Because the function's going to end in terms of x and y. Does that make sense? Now solve it. Do something. Just subtract the 3 or something. So we got x minus 2y is greater than, yeah, I flipped it around. X minus 2y is greater than negative 3. Does that make sense? So we found continuity. This will be continuous on all ordered pairs x, y, such that x minus 2y is greater than negative 3. So what we do is we figure out continuity. If it's all real numbers, great. All ordered pairs, I should say. Figure out continuity here. If it's not, just set the parameter equal to what you're plugging in for that parameter. And then you have this inequality. Solve for the inequality. And you have the domain and the continuity for that second composed function. Head nod if you're okay with that one. Now, last one. This is going to be the opposite case. Let's start here. Is this continuous on all t? Yes or no? Is this continuous everywhere?
No.
Notice its tangent. Is it continuous on all x?
Yeah.
Continuous on all y?
No.
What's wrong with it? Asymptotes where?
I
All values of pi over 2. So we have, this is continuous on ordered pairs x, y, such that x I don't care about. X is good, but I just can't have y equaling pi over 2. I can't have y equal to pi over 2 or any multiple of that. So we're going to say plus k pi. And what that says is if you add or subtract pi to it, you still have a problem. Any multiple where k is an integer, pi, you go, okay, so negative pi over 2, or 3 pi over 2, or any circle, any like half circle around there. You can't have any of those. Now, here's the deal. Here's the deal. Watch carefully. If I want to talk about this, here's what I want you to see. This is going to be in terms of xy, correct? Is this going to add any more continuity issues to this situation? So this added, okay, this said I have continuity issues, I didn't. So we have to set it equal to this continuity issue, and we have to figure it out. If I say I'm taking this whole thing, and I'm just going to substitute this in for t, this doesn't add any more problems. All it says is that, yeah, you're going to have continuity basically the same region you had this. This was the only problem there. It was already in terms of x's and y's, so it's going to be this exact same value of points. Does that make sense to you? The cosine's continuous everywhere. It's not making a difference for us. It's this piece that even when I put it here, I still can't have the y equaling those multiples of pi over 2. Do you guys catch that? So composing, you basically keep the same continuity. Sometimes you have to work with it and say, okay, well, my t's are changing to x's and y's. Figure that out. But for the most part, you just take continuity from both of them and kind of jam them together. That's basically what we're doing. So this says continuous everywhere. That means I'm not going to have any issues when I plug into this function. If I'm not going to have any issues when I plug into this function, we look at this function. I go, okay, this is what I'm plugging into that. Where is this not continuous? Well, it's continuous everywhere except this. Therefore, since this doesn't create any more issues, this is also continuous everywhere except that. Should fans feel okay with that one? Okay, I promised you this. I promised that we were going to talk about the squeeze theorem. I'm going to show you one example. I said, you know, when we started this, I said it's really, really hard to prove that limits exist. It's really easy to prove they don't exist. We spent most of the time doing that. How we prove limits exist is by using continuity and just plugging in the number that uses continuity. We talked about that a little bit. We said if a function is defined, then it's got continuity. If it's got continuity, the limit exists. So just plug the number in. And if the function is defined there, then it's continuous there. We talked about the region. We talked about how if we're defined and we plug that point in over the defined region, that we find a neighborhood of points and we're continuous there. The limit has to exist. So if we're defined, continuity, no problem. Just plug the number and you got it. Well, what if we can't do that? And what if the limit still exists and we didn't have the magic trick of polar? This is the case that you use. So if we don't have that stuff, for example, let's talk about this limit, only one. First thing you should always do with limits is what? Plug it in. And you plug it in, you get 0 over 0. You can verify that form if you want to. And then we go, okay, we're used to saying things don't exist in this case, but this one does. How do you prove it? You might try polar and see what that gives you. You could try it. That might work. I don't know. I want to show you in this case how to use a squeeze theorem to your advantage. This is the other way. So the things we do with limits. First, plug it in. If you can plug it in and you get a number, then the function's defined there, which means we're continuous there. We just plug it in and we're good. Because if we're continuous, the limit exists. Got it. That's fantastic. Or we try to prove it doesn't exist by finding those different paths. We spent most of our time doing that. Or using the polar trick that we created. That was pretty cool. Or the squeeze theorem. Those are basically the things we do with limits. I'm going to show you the squeeze theorem right now. So let's take a look at this. Let's look at our function. And I want to consider the absolute value of the function. Like, where are you getting that from? I'll show you where. I'll show you where in a second. True or false? This denominator is always positive no matter what. The absolute value doesn't really matter. True or false? 5x squared is always positive no matter what.
Yes.
That doesn't really matter. True or false? Y is positive no matter what.
Yeah.
False. So this would equal 5x squared over x squared plus y squared, absolute value of y. Does that make sense to you? Now we're going to build some stuff here. I don't want to confuse you, but we're going to build from scratch and try to get back to this thing. So we're going to try to get here. So here we go. This is going to seem kind of nonsense, but you understand this, right? That this is equal to 5. 5x squared plus x squared is equal to 5. You go, okay, why are we doing that? Well, that implies this. If I add anything to the denominator, if this equals 5, and I add something that's greater than or equal to 0 here, is it still equal to 5? What would it be?
Smaller than 5.
Smaller than, or if it's 0, it would be equal to 5. Does that make sense? True or false? Y squared is greater than or equal to 0. So since y squared is greater than or equal to 0, if this equals 5, and I add something to the denominator, I make the denominator bigger, I make the fraction smaller, it's got to be less than 5, or at most equal to 5. Head nod if you're okay with that one. Okay, we're going to use that in a second. Now, this is why we have to have the absolute value. You know I can do anything I want to with inequalities as long as I do it to both sides. And if I multiply by a negative, I've got to flip them, right? Do you know that? Okay. I'm going to multiply by y. Now that's a problem. It's a problem if I do this. What's the problem? If I multiply by just times this by y and times this by y, that's a problem. Because y could be positive, y could be negative, I wouldn't know, I wouldn't have a correct inequality. That would be a big, big situation. Does that make sense? However, if I force this thing to be absolute value, now I'm multiplying by what type of number? For sure positive. Do I have to flippy dippy the inequalities? No. Okay, what it gives us is 5x squared absolute value y, oh my gosh, over x squared plus y squared is less than or equal to 5 absolute value of y. Can I have an honest show of hands if you feel okay with this so far? This is the reason why we needed the absolute value, was so that I could multiply by something and not flip that inequality and get the same thing out of it. Do you guys get the idea? That's why I needed that. Now, let's think about this. Tell me something. We're going to start with this. Tell me something about... Tell me one thing about that you know. It's on the board already. Tell me one thing about that you know.
Always positive.
It is always positive. So it's greater than 0. Tell me the other thing that we just found out. Say that again. How the squeeze theorem works is this. It says if you take the limit of this and you take the limit of this and they go to the same number, the thing squeezed, or sandwich theorem, some people call it, the thing sandwiched or squeezed between them has to go to the same value. What's the limit of 0 as x, y approaches? I don't even care. Come on, it's not your question. What is it?
0.
And what's the limit of 5 absolute value of y as x, y approaches 0, 0? Notice there's no x, but I don't even care. What's it go to? By the squeeze theorem, since the limit of this function goes to 0 and the limit of this function goes to 0, the limit of this function by the squeeze theorem. 0, 0, we built it. 0, 0, middle's got to be 0. Now, we haven't proved a darn thing right now, but we're about to. You guys okay with this? You sure? No?
Yes.
I want you to look back at this piece. This piece is equal to that piece. Do you guys follow that? Yeah, no? Therefore, the limit of the absolute value of all this junk is 0. And you go, awesome. But wait, Leonard. Wait, though, Leonard. Is this exactly the same as that? No. No. But this is why we had statement number 3 over here like 25 minutes ago. It was this. Continuity holds for compositions of continuous functions. Here's my question to you. Is the absolute value function a continuous function?
Yes.
Do you see that this is a composition of this crappy function inside the absolute value function? Do you guys see that?
Yes.
Continuity holds. That means we can do this stuff with it. But the big point here says that means that this limit equals the absolute value of the limit of 5x squared y, x squared plus y squared. X, y, 0, 0. We go, awesome. That's the same thing. Absolute value of 0 is 0. We get the same exact thing. So we have this composition of continuous functions. We prove that limit exists by the squeeze theorem. I got to stop it right here, and we're going to call it good on this section.